title. So, in the previous lecture we discussed a simple model of directed Sandpiles, where everything seemed quite straightforward. Every site was, it was a two-dimensional directed model of Sandpiles, and you can calculate the avalanche statistics and stuff like that easily. So, of course, the important question is whether what one learns there can be extended to other models or other problems or more general real systems. So, lot of variations of Sandpile models have been studied, and the first variation was the Mana model. I think this is 1991, soon after the model of Bachtang and Wiesenfeld. And what Mana said was that, well, let us work in 2 dimensions, but if at each side the height variables can take values 0 to 3, that is a lot. So, can we make the model simpler? So, he said let us consider a model where the maximum height is 2, sorry, allowed heights are 0 and 1, and the 2 is already unstable. And so, if at one side the height 2 occurs, then 2 particles leave, but it has 4 neighbors. So, where will they go? So, he said they go at random, they just pick each particle, when it leaves it goes in a random direction in one of the 4 directions possible. Okay. So, these are more generally these are called stochastic toppling rules. So, you can pick your favorite height and you can pick favorite toppling rules, and then you can study these models and see if they behave in the same way as the deterministic toppling rules, where once a toppling occurs exactly what will happen next. And it turns out that these models behave differently than the standard BTW model. If you make the toppling rule stochastic, then the qualitative behavior of the model or the critical behavior changes. Okay. So, well, unfortunately the exact values of the corresponding exponents are not yet known, and so this model is well defined. It seems to be easier to analyze numerically than the BTW model, but the analysis is not well understood. So, then we were thinking of other variations. So, we said adding stickiness to grains. This was called the well, okay, let me write it like this. It is not exactly this, but something like this. So, people did some experiments with real rice, and it turns out that it has also forms a pile and does some behavior, but the rice grains are of course elongated, and then it depends on how the grain gets deposited. Okay. So, even the critical height may depend on the local geometry, and it may not always be the same. If the grains sit in some way slightly vertical, then fewer grains will become more unstable or some such thing. So, we thought let us see if we can understand this model. So, this was so let us consider this model. It is defined like this here. same basic geometry let us keep unchanged, and the rule is that if a particle comes and height is greater than or equal to 2, then two particles leave. With probability p. Or else grain just stays there. And it is stable. You know, sometimes it can stick and sometimes it can topple. So, once it stays there, then until the next grain comes and sort of perturbs it, it just stays there. This was the rule. And the question is, does it make a difference to the behavior of the pile? Okay, so, I guess case when p is 1 is easy to understand, that is the old problem which we already understood, right. When p equal to 1, it reduces to the previously studied model. Yeah, so let us say add particles only at top. That is not a very important restriction, but for the moment let us put this in. So, what happens when p is 0? When p is 0, you just add particles on top, they stick there, and so the height there keeps on rising, nothing goes down. Okay, so, there is a pile up of particles on the top layer and there is no steady state, because the thing just keeps rising. Suppose p is 0.1, then what will happen? Well, you add particles, when one particle comes in, on the average 0.2 particles leave, because the height will become rather big. So, the height condition will be satisfied, but then with probability 0.1 you will throw out 2 particles, with great probability you will let it stick, right. So, it says that for small p, there is pile up and no steady state. For large p, I guess, certainly for p equal to 1, there is a steady state. So, here is my system, this is p equal, this is p equal to, this is probability p equal to 0, p equal to 1. In this region there is pile up and there is no steady state, somewhere here there is a steady state and there is a p star, which is the critical probability above which you can get a steady state. Okay. So, what is this p star? Can one understand that? Okay. So, let us see. Let me take a file. Now, when I decrease p, the mean height of the pile keeps on increasing, because you know there is more stickiness, more grains stick. At this point, there will be very large number of particles per site, and beyond this it is infinite number in the steady state, if there were a steady state to be reached, it is not reached. Okay. So, if I am very close to here, there will be very few grains on the top layer where the height will be small or close to 0. Most of the sites will have already some particle there. Okay. So, when I add a grain, it will topple with probability p, and then so I add a grain here, it topples with probability p, it sends a particle down, then this one will also topple with probability p, because this one is also quite full, right, and then this one will also topple with probability p. These will send particles down here, 2 particles will come in, but with probability p they will topple. Okay. So, what is the value of p such that such an avalanche can reach arbitrarily far down? What is the lowest value of p such that this avalanche can reach arbitrarily far down? That is the directed site percolation threshold on this lattice, because this is a directed site percolation process. If you start here with probability p, this gets infected. If any of these 2 neighbors are infected, this guy gets infected with probability p, and so on. Okay. So, we get this very interesting result that p star is the directed site percolation threshold on the square lattice. Okay. So, now what is the statistics of avalanches in this case at the point p star? Well, it is the statistics of percolation clusters, because this site whether the site topples or not is like the infection process, and it is like asking, if I start with a single infected individual, what is the progress of infection in the system at critical threshold. So, those answers are all known, and all the exponents of avalanches, the transverse size, longitudinal size, all these kinds of stuff are percolation exponents. So, it says that the exponents of Sandpiles in this problem will be the percolation exponents. Okay. What happens if you go somewhere here, slightly away from p star? If you go slightly away from p star, then the things topple with probability bigger than the percolation threshold, and then roughly speaking what you will get will be supercritical clusters. So, a lot of particles will go down, but when lot of particles go down, then the density here becomes lower. Once the density becomes lower, a few sites will appear where the heights will be 0. Then when you add something, then nothing will topple. Okay. So, the density of particles on the top will organize itself to have a value such that the clusters will be able to not be supercritical, will not send too many particles down, but will be able to reach to the bottom. They will be critical. Okay. So, the density in this problem at this point will organize itself to be at the critical point. Okay. In fact, it turns out that there is a density profile which develops in this system, which is such that, so you want the density profile to be such that when you add something, it does not cause a pile up, and also it does not cause an infinite avalanche. So, it has to be critical. So, this is the self organized critical part, and now what are the exponents of the avalanche clusters in this regime? This I will not be able to do here. In fact, we could not prove it rigorously, but it turns out they are all dp exponents. So, on this entire line, the exponent of the avalanche distribution is dp exponents, only at the end point it is different. Okay. So, this was an interesting sort of observation. It said that there is a connection between the Sandpile problems and the directed percolation problem, and you get dP exponents in the Sandpile model. So, this particular conclusion, of course, we did a little bit more, we added some dissipation and stuff, but let us not worry about that. So, this was a paper which we wrote in 2002 with Pradeep Mohanty. So, this is 2002 PK Mohanty. So, for the directed model, this result follows, this we showed, but then we said that okay, but now what happens if the model is undirected. So, based on some numerical data and some guesswork, we argued that maybe even those things are dP like. The clusters, the statistics of avalanche clusters is the same as the statistics of dP, and we were influenced by the idea that this dP class is very robust, and everything flows into dP at some stage. If you have some complicated infection process, we do not care what are the details of the infection process, in the end it looks like dP. So, of course, we knew that there is a difference here which was pointed out by everybody, which is that there is a conservation of sand, So, this is a dP with conservation of sand. So, how can it be the same exponents as dP without conservation of sand? dP is directed percolation, and so why does it happen here that you get the exponents which are characteristic of directed percolation even though there is conservation of sand in the problem. Okay. So, that answer is actually rather easy to see. It is the following, that what happens here is that when you add a grain, the avalanche activity travels down, and if one or two particles leave here, then the height here becomes less, that is the conservation, but that affects the next avalanche. Suppose the height here was unchanged, it will not affect the properties of this avalanche, it will only affect the properties of next avalanche. So, the single avalanche properties do not feel the conservation law because of our special dynamics. We said you start here, then topple them, and then go layer by layer down, and by construction the conservation law does not come into force, does not matter to you much. Okay. The argument is sort of like this, that suppose a person has some money, 500 rupees does not get you very far, 5,000 rupees, and you are traveling. So, you go to some shop, you spend some money, then you go to another shop, you spend some money, and eventually the fact that the money is conserved, all the currency notes you carried are now in the various shops. Okay. So, then of course, at some stage you do not have any money and you will stop. That is like the grains which will stop, or the avalanche which will stop because it has exhausted itself in some way. And the fact that the person has stopped is visible in the fact that all these currency notes are there in all the trail of the shops he visited. Okay. But now suppose he has a credit card, then what happens? Well, he can just go on doing the same thing, and all these people, let us say in some sense they have some IOU coupons which they will encash later if necessary, but right now they just have a piece of paper, I took some money, black, some slips of paper. So, the conservation law is still there in some sense, but it does not matter to the person, he just keeps on going spending money, right. The conservation law will matter only if these IOUs can affect the motion of the person in some way. Like if there is a limit on how much money you can spend, then at some stage it will hit you and you will not be able to spend. But if there is no mechanism in the model for these IOUs to affect your subsequent motion, then whether the money is conserved or not conserved does not make any difference. Okay. So, that was our argument. Now, how does this argument work in the context where there is actually no preferred direction of motion. So, in the directed models this argument is good, it works. In undirected models where the avalanche can come back, then of course, next time you come back that person will say, but you already have, I have some IOU from you and so on. Maybe he does not give you any more credit. But we said, or we thought that a typical avalanche does not always come back. So, this conservation law, even if it works, it does not work perfectly, and a conservation law which does not work perfectly is not a conservation law. Okay. So, we felt that it is certainly plausible or possible that even in the presence of conservation law, the exponents can be dp like, because they do not affect the motion of that avalanche. They will matter in the long time limit if you look at the total number of sand grains in the pile or some such thing, but they will not affect the motion, they will not show up in the single avalanche statistics all the time. So, we wrote up some paper, then lot of people wrote other papers where they felt, they showed numerical evidence saying that no, the exponents in the Mana model are very different from the exponents in the directed percolation. But these exponents are actually not so different. One of them is 0.141 and 0.115, they are around one of those exponents is like that, and it is not so different, it differs in the second place of decimal. Then you have to worry about how you analyze that data, and the issue sort of was unsettled, but generally veering towards the idea that for undirected Sandpile models the exponents are actually different than dp. Okay. Then there was a sort of theoretical discussion of this idea, which let me discuss. So, this is so this is field theory approach to studying sandpiles. Okay, so let me start by some statement which I will make, but that is slightly subjective. So, the field theory technique is usually believed to be some kind of a coarse grained description of the actual dynamics, and if you handle all the, so it is typically non-rigorous. You have to wave your hands, you have to say, oh, I kept these terms, all the other terms which I did not keep, they are irrelevant, they do not matter, you can do what you like with them. They are also plagued with infinities, plagued with divergences, ultraviolet and infrared, both kinds. Okay. Now, there is some general theory of Wilson which says that you can actually produce a nice theory starting with well regular field theory by proper coarse graining procedure, but in most of the applications that procedure is not really shown to be true. There is a hope that whatever I am doing will be regularized later. Okay. So, let us see what kinds of descriptions people make for field theories. So, I thought I will make this comment. So, when I read those field theory papers, my general feeling is like, there are papers which prove the existence of God. So, if you believe it already, then the argument makes perfect sense, the final conclusion is also true and clear, and so everything is okay. If you do not believe the final answer, then even the argument does not seem to make sense, it uses words which you do not fully understand. Okay. So let us see how does it go. So they said there is an activity field rho of x t. So what it does, see, this is non-equilibrium problem, so there is not going to be any Hamiltonian, but we can write down an equation of motion of this field. So the equation of motion looks like this: d rho by dt is equal to some term which is linear in rho. This coefficient is, the rate at which things changes depends on how many people are there. So it is birth minus death. Some of these individuals will be dying, but some more will be born, and it is a difference between the birth and death rate, and it can be positive or negative. Okay. Then there is a term like rho squared, which is sort of said to be the saturation effect. Okay. And then there is a term like del squared rho, which, so this is saturation. It says that there will be some asymptotic value which will be reached, things do not keep on going linearly. And this is diffusion, and then there is noise, because these do not obey deterministic equations of motion, you have to have noise. So let us call that noise equal to eta of x t, and then you have to write eta of x t average is equal to 0, but eta of x t, eta of x prime t prime, well, they are delta correlated in space and time, but in addition they have some dependence on rho itself. Like when the activity is 0, then the noise also has to be 0. So the usual way this is said is that it is proportional to rho x t. So this is the standard equation for directed percolation.
What does this
saturation term mean? This was so people studied this equation, it is called logistic equation, d rho by dt is equal to a rho minus b rho squared. If you solve this equation, it has a solution like this. If you b is 0, then it just keeps on growing exponentially fast. Okay. So it just says that too many people cannot be supported. If the population becomes too much, then the rate of dying increases or some such thing. Okay. It disfavors too large values of rho. If rho becomes too large, d rho by dt becomes negative. Okay. So this is kind of well studied. Actually, the field theory for this stuff was worked out by Janssen in 70 or some such thing, but people have complained about that treatment even later, because they said that okay, you can develop this and you can develop all kinds of perturbation theory, but the theory works only if you can identify all the relevant quantities in the problem. But in this kind of percolation problem, there may be other marginal operators. If they are there, then whatever fixed point you study may not work, and so on. Those sound like technical objections, but they came even several years after the original stuff, and people have not been, it is not very clear that we have a good field theory for directed percolation even now, fully satisfactory. Okay. All right. So now I have conservation of grains. So what should I do? Well, they said, well, let us put in another variable called phi, which is equal to density of grains. So, there are two kinds of stuff. One is the activity, which is the amount of toppling which is occurring at a point. The other is variable called phi, which is the density of grains. Then I got to write an equation d phi by dt. Then one says that, oh well, what will it do if some particles are born here, then the density of grain will decrease. So, roughly speaking, whatever comes here in the positive sign comes here in a negative sign. It cannot be fully local. So, let us just say del squared rho. Because this is the total density of grains, active or passive, toppling or non-toppling. Then the only way it can change is because of other people coming from outside, that must be del squared rho. In the original treatments, people have added other terms like plus rho minus rho squared plus eta of rho, eta of phi, noise term. But then one feels that maybe these are not necessary, because that is a redefinition of phi. Phi I defined in some way, not very clear what it means. So, if it is the total number of grains, then maybe these terms are not there, because even if some grains change from active to passive, it does not change phi. So, if I redefine phi like that, these terms may be dropped. There is also no noise in phi. Okay. This is of course not good enough, because there is no coupling. Equation for rho does not care for phi, that is what we started out by. So, you have to couple them in some way. So, they said that the most reasonable coupling is rho times phi. Add a term like that. Why should it be this term, why not some other term? They said, well, you can write down whatever term you like, but it does not matter, the details do not matter, they all become the same, they have the same effect. Okay. So, let us keep this rho times phi term. Then this equation is easy to solve, because it is d phi by dt is equal to del squared rho, rho is somebody else. So, the evolution equation for phi is easily solved. This says that phi of x t is equal to phi of x at t equal to 0 plus integral dt prime del squared rho of x t prime. Okay. That is not a problem, that is straightforward, immediate. Then I can put this in here and I get an equation in rho, but now it is an horrible messy local equation in time, because these terms are local, but this term involves integral over all the previous time history of the rho field. And such kinds of field theories are very ill behaved in general. Whatever intuition you have developed in the past about field theories may not always work in the presence of such non-local terms. Okay. And so, that is where it kind of stays. One can say that it does not work, but then somebody else will say, no, 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 this does not really cause any problem, let me go ahead, and then you do something, and then you find that the exponents are actually different. Okay. Then in 2012, there was a paper by Mahashweta Basu, U Basu, Mohanty and Hendrickson. And what they did was they reanalyzed the existing data on these Sandpile models at the critical point. So, they are studying fixed energy sandpiles. They are this mana type, in the sense they are random transfer of particles, undirected. And so, what one typically does is you take a lattice and you put in some number of particles at random and you evolve using the mana rules, and if the initial density is too low, eventually you find that the thing gets stuck, nothing happens. Then you try with some other initial condition at the same density. At low enough density, everything gets stuck, there is no problem. Then you increase the density. Then they take longer to relax, eventually everything dies. Then you go to even higher density, and at some density you are able to find that the activity keeps on going further. So, you expect something like this, rho as a function of, this is this is activity as a function of time. So, the density will go down to 0 in some cases, and it will go to non-zero value for rho greater than rho star, and then you can see how much it is, and estimate the critical point and stuff like that. But what they found was that when they started with some initial conditions, the typical behavior of the density was like this. Sorry. Was like this. So, it is a non-monotonic approach to steady state value. It is not impossible, it is nothing about this, it depends on the initial condition. You start with some initial condition, then you have this behavior. If you started with some other initial condition, I guess you will not have this behavior, and if you started with some condition like this, then it might even stay constant. Okay. However, these initial conditions are actually the random initial conditions, where each particle is initially added at random site with a given density, and then you have to analyze data to see when the thing goes to 0. So, it becomes difficult numerically to estimate the critical threshold because of the non-monotonicity. And if you change the critical threshold even on the third place of decimal, the exponents change by a much bigger amount. So, using very careful numerical tests, they concluded that no, the previous estimate of exponents values have to be revised, and they are closer to dp values. Okay. So, well, this is numerical study in the end, and while you may like it or you may not like it, one cannot be perfectly sure of the outcome, because always somebody else can do even better study and maybe revise the conclusions again. But anyway, that is what it was. So, one could leave it like that, but they found something more interesting in addition, which is called well, it is actually more or less natural initial conditions. So, they found that if you start with random initial conditions, then you get this overshoot and it causes lots of problems in data analysis. But a much better way to analyze data is to start with some sandpile and let it run, and then increase the density by a little bit by adding a few grains and let it run further. Do not start all over again, do not start with the random initial condition. They called it natural initial. What is happening here is that with random initial condition, there is some system, it evolves, it builds up some special correlations in the steady state, and once those correlations are built, then it can reach some regular steady state value. If you restart with initial, then you have to wait longer to build the initial conditions, but if you start with the previously prepared initial condition, more or less it is right, then you just add a little bit perturbation, then you do better. You save on computer time, let us say. Okay. So, there is a notion of natural initial condition versus the random initial condition. And so, what is this natural initial condition? So, this is now realized to be an important issue, is called hyper uniformity. And what it says is the following, that I go into this system and I go into the steady state, and then I look at integral rho x t dv over a finite volume V in part of the system. I go into some part and I see how much activity there is. So, of course, it will vary, and I calculate the variance of this quantity. Okay. So, normally you would expect that this variance will be proportional to the volume of the system if the things are uncorrelated at large distances. Okay. But it turns out that in all these studies they found that they are not, this grows slower than the volume, which says that the density of the particles and density of the activity has long range correlations which are more than very strong anti correlations in the density. Okay. Now, the point was that the standard field theory treatment with rho phi whatever, you can worry about the details, but phi correlator at large distances there is small. So, the standard field theory treatment cannot take into account the hyper uniformity. Hyper uniformity implies long range correlations in the phi fields, which more or less the theory does not allow. Okay. So, then if you want to allow for, if you want to say that these fields are correlated at large distances, that means there is an effective interaction between them at large distances. If there is a depletion of density here, there is a depletion of density here, there must be some effective interaction between these depletions, then you have to write that term in the effective Hamiltonian, which will again be very non-local and very messy. And so, that puts into doubt the whole framework of this field theoretical description. It works very well if it is some local interactions involved, but if the interactions are non-local, and if also it involves being able to identify all the relevant perturbations. Now, I have a good hope that whatever I wrote down is all that matters, but I cannot be sure, especially in self organized systems. The system always goes into a steady state, critical state, and it remains critical. So, it does not get out of criticality easily. So, most of the perturbations are marginal as opposed to relevant. Okay. So, then it makes it difficult to take this approach very seriously and push it very hard. So, I thought maybe one should do something else, and so we decided to take the same model, but have a different perturbation on the simple model we studied already, and see if we can make some lattice model where you can study these issues. Okay, so this is a lattice model with random critical heights. So, this model is defined like this, the same lattice, we do not want to fiddle with the problem too much. Okay, but now the rule is this, at each site you can have some particles, but when a toppling occurs, after the toppling the critical height, which is how many grains can be supported at that site, is chosen again, randomly reset to a new value independent of history. So, the height can be 2 or 3, which is randomly decided after the previous toppling has occurred. So, critical height is reset to value 2 or 3 randomly independent of previous history, that site and other sites with probabilities p and 1 minus p. Okay. So, now if I look at this system, site 3 will always topple, and when it topples it sends 2 grains down, but a site 2 may topple or may just stay put. Okay, that is the rule. So, if I look at a stable configuration, the heights will be 0, 1, 2, allowed stable heights. So, I do the same thing, I run the, I keep on adding particles, I let them topple, let them go away from the bottom, I go into the steady state, and then I ask what are the probabilities of different configurations in the steady state, because that is what will help me determine the statistics of avalanches later. Okay, it is the same question as before, you just want to determine what is the steady state of this system now. Okay. So, well, this problem is not so easy, but let us take, suppose I have a single site, then what happens? Well, it can have height 0, then I add a particle, it becomes 1, then I add a particle, it becomes 2. So, let us draw it like this, there is a configuration with h equal to 0, it goes into a configuration with h equal to 1, h equal to 1 can go into a configuration with h equal to 2, or it may go to a configuration with h equal to 0, because what happens is that the height which is randomly reset when you add the particle may be 2. So, if it is already 1, it becomes 2, then 2 particles leave, it goes to 0, but if it is reset to 3, it's reset to 3, then 2 particles will not be unstable and will remain 2. So, what happens is that the heights, but if you start with 2 and you add a grain, then it will always go back to 1 with probability 1, and if you start with 0, then it goes to 1 with probability 1, but this occurs with probability p, this occurs with probability q. Okay. So, it is easy to realize this one, there is a steady state, and the steady state is given by this vector p by 2 times 0 plus half q by 2 times 2. Phi I means the steady state at site I, 0 I means the height is 0 at this point, 1 I means at site I the height is 1. Is that notation clear? Okay, and you can check that this is the steady state. Okay. This one is half, this is p plus q is 1, so they all add up to 1, it is a proper probability vector, no problem. Now, suppose I have a whole row of sites like this, then when these sites I evolve, they evolve independently. because I add here, it does not affect the rest, they only throw grains down. So, it is clear that the steady state for a row for phi of rho is equal to product over I phi of I, all sides within the same row, you just multiply them, they are independent. Okay. And this phi has a nice property that if I add the grain anywhere on this layer, then phi does not change after. So, adding a grain is some operator of add a grain acting on phi. It is a linear operator clearly, because it is acting on the space of probability vectors, will be just phi. It is a steady state. Okay. Now, suppose I have two layers, then the steady state for the top layer is just this, because it does not care what happens below, right. But so this, so steady state for this two layer system will be product will be phi rho 1 multiplied by this is a direct product phi rho 2. It is also a product, because if I add something, it throws some things down on phi rho 2, but anything adding on rho 2 does not change it, it will remain unchanged. So, this simple product ansatz is still working. The only problem is now I have height 0, 1, 2 with probabilities these numbers. So, I can still again study the statistics of avalanches in this case and see what happens. Okay. So, yeah, okay, I have. So, actually the model is rather simple and straightforward, and let me describe it in a different way now. So, I will say that look, I have a layer which in our case is called time t. At time t there is an activity at each site which is nxt. There are different sites, and this site has toppled n times, and the n site x has toppled nx times on this layer. Okay. And I want to determine what will be the toppling in the next layer. So, I want to determine this function n of x t plus 1 for all x and t, for all x for t plus 1. So, what do? I go to a particular site, it has some grains coming from left, some grains coming from right. The grains coming from left are n of x minus 1 t, the grains coming from right is n of x plus 1 t. Then there are some grains here originally, but that is a independent random variable. So, I decide now how many grains are going to be there plus delta z of x t plus 1. Then I decide what is the threshold here, because that is also randomly reset, right. And then I say how many grains are going to stay and how many grains are going to leave. It is a very local operation. So, given nxt, I can determine nx t plus 1, and there is a noise term inside which depends on this and the local noise threshold which I can reset. And so, I can evolve these avalanches and I can see how they work, and so I have an equation n x t plus 1 is equal to 1 upon 2 n x minus 1 t This noise has some properties which I will have to determine, but it is easy to check using this stuff that this, let us call it n in, this is the number of particles coming in. It matters if this number is odd or even, because then you have different behavior. If n in is odd, then eta is equal to plus minus half with some probability, which depends on this p and q. If n is even, eta is equal to 0 or plus minus 1 with some probabilities, and these are such that this n will be an integer if these n's were integers. So, everything is working out. I know these probabilities. So, I determine this eta and I evolve it and I get there, no problem. Okay. So, I can hope to determine the statistics of avalanches in this model. But we thought that let us be more ambitious. So, let us work in a more general background. Let us start with a background in which there is C0 concentration of height 0, C alpha is concentration of height alpha, with alpha is 0, 1, 2. Of course, C0 plus C1 plus C2 should be 1, and then I will prepare a background with a given concentration, and then I add a single perturbation one side and see how it evolves. And okay, so what happens? Well, this picture so I think we would like to draw it like this. This is 0, 1, 2. This is a triangle in which at this point the concentration is 0, at this point the everything is 1, everything is 2. At this point the distance from this line is the concentration of site 2. So, this is C2, C1 and C0, and the sum of these three terms is always 1, and that is my representation of the concentration as in a triangle. Okay. So, now let me erase this part. This is clear, this represents everything is 0, everything is 1 on this line, there is just a mixture of 1 and 0, but no 2, on this point it is only 2 and so on. Okay. So, I also have a parameter small p, which is the toppling probability. So, let us put it down here, and so this p varies from 0 to 1. So, every point in this prism now represents a possible starting initial condition and starting choice of p, and then I will add a particle and see what happens to the activity. Okay. So, what will happen to the activity? Well, if you have too few particles, then the activity will die. If you have too many particles, the activity will grow. So, there is a regime in this prism which is subcritical, and there is a regime which is supercritical, and there is a boundary between these, which is the critical surface, right. So, with a little bit of work, one can try to figure out what that surface looks like. Looks like this. Let me not draw it in great detail just now. There is a surface. This is the finite avalanche regime, and this is the infinite avalanche. Everything is 2 and toppling probability is 1, you add something, a big avalanche will occur, and this is the critical surface. Okay. If you pick a particular value of p that cuts a section on this surface, and then you drive the system long and long, eventually it will settle into some particular point, because the concentrations will readjust to their favorite value. So, there will be a particular point for each p, and so there is a line on this critical surface which is the SOC line, self organized critical line. That is, the points will lie on this line if you drive the system for long. And so, now my job is to determine the behavior of what happens to the avalanche statistics on this critical surface and on these critical lines. Okay. So, that does not look so simple until you realize that on this surface there are looks like a very complicated stuff with 3-dimensional phase diagram, but there are lots of points which are very nice and special points where you can determine the behavior of avalanches easily. So, let us just first we start by naming them. So, this point is called A, and this point is called B, and this point is called C. So, consider the point A, that is C1 equal to half, C0 equal to half, C2 equal to 0, P equal to 1. So, what is this model? This model is the model where you always reset to height 2. The critical probability is the reset critical height is always 2. So, that was the model we had already discussed before. 0, 1 are the possible heights, half is the average value, sorry, with every half is the concentration, each occurs with probability half. So, this point, the avalanche statistics is what we have already discussed. So, I know what it is. What happens at point C? Well, C is the point where you always reset to 2, P is 0. So, then it is correct, but it is sort of written in bad order. So, now C1 is half and C2 is half and C1 is C0 is 0. It is the same problem, but only 1 2 exchange for 0 1. And so, this point also has the same behavior as the simple process we have already studied. Okay. What about the point B? So, at the point B, B is the point where everything is 1, it is on the line 1. So, C1 is 1, C2 is 0, C0 is also 0, but P is not 0 or 1, it is some other value. So, what is it? Turns out that it is half. So, what happens if all the sites have height 1? Let me continue this picture. So, all sites have height 1, right, but when I come to a site, I decide whether to topple or not with whether the critical height is 2 or 3 there. Okay. So, I start here, with some probability this site will topple, with some probability it will not topple, with probability half it will topple. What will happen? what is the probability it will not, it will stop right there. That is that this particle will send one particle down here, but that should not cause anything. So, that will occur with probability half if you choose the wrong value of critical height here, and similarly here. And you can work out these probabilities, you can convince yourself that the statistics at point B is also the same direct, the simple model we have already studied. So, all these 3 points have the same critical behavior. What about this line? Rest of the points on this line. This one actually it is hard to study in great detail, but we found by numerical tests that these are actually dp like, all the exponents on this line are dp like. Then there is this line, there is this point D. What is the point D? Well, D is a point in which the heights are 0 and 2, but the toppling threshold is always set to 2. So, you can check again that in this case actually this is a directed percolation, side percolation process. So, I also know what is the coordinate of D, that is the side percolation threshold, side percolation, directed percolation for square lattice, and I know what are the statistics of avalanches on this point, this directed percolation. Okay. And so, then I can try to determine for the rest. Let me not go through that kind of exercise. It is easy, but it is tough to do it in the board on the last day of the week. So, let me just draw the picture schematically here. So, you have a sort of a hexagon like this, A, B, C, D, E, F. This is the critical surface redrawn, and I know the behavior here, and I know the behavior here, and I know the behavior here. These are like what we discussed already, the simple directed Sandpile model. The behavior on this line is directed percolation like, the behavior on this line is directed percolation like, the behavior on these 2 other lines is very interesting. It has not been studied so far, new. It is a different behavior. And then what about the full surface? The behavior in this entire surface is the same critical exponents, and it is different. It is a SOC behavior. So, in this very simple model, you get different kinds of critical behavior at different points in the parameter space. Okay. So, that sounds a bit confusing, but actually it is not. So, this is a fixed point of, there is a particular behavior which occurs here, but this behavior is unstable to perturbation. So, if you make a perturbation, there is a flow away from this fixed point to this other fixed point F, and along this line there is some other fixed point which is the dp fixed point. So, any point on this line will flow into that fixed point. Any point on this will flow into a fixed point F, like that, and this one flows into a fixed point which we can call this one D, and all of this here flows into like that. Okay. even that one is a little bit messy, but you realize that this point and this point and this point are actually the same. So, if I take the Ising model and I did the low temperature fixed point of the Ising model, there is a magnetization up fixed point and there is a magnetization down fixed point, but they are actually the same. So, I can identify them. So, if I identify A, B and C and this blue, then I get a simple fixed point and this F and that F, sorry, they should be marked consistently. So, this point and this point, I get a much simpler flow diagram A, F, D, S. So, this is the simple model we studied first. This is the directed percolation. This is this new fixed point and this is the SOC fixed point. And so you see all these different behaviors, then it is very easy to realize that in numerical simulations, if you have 4 different competing fixed points, then interpretation of data is going to be non-trivial. Okay. So, I am happy to stop here instead of continuing for longer. So, I can ask you if you have any questions, and there are some technical details about the values of exponents at various points, but those I will not get into now. So, any questions about whatever was said so far? Okay, no questions. So, let me just make some additional comments. So, once I know this much, I can go back to the field theory description and see how far it is working. All the assumptions which people made, which seemed obvious to them, are they actually true or not true? Okay. So, let me do that. So, we started with these two equations, d rho by dt is equal to epsilon rho minus rho squared plus del squared rho plus noise eta. Oh, sorry. Plus eta phi. That was the new coupling which we introduced. There are everything has a coefficient in front which I am not writing. D phi by dt is equal to del squared rho is what we wrote. That is all. Okay. So, let us look at the equation for rho. Rho was my activity. So, in this model there was actually an equation for rho, which was in this n of x t plus 1, which was an exact equation. It has a noise term, but it does not have a quadratic term in it. The field is fully linear. Okay. That is because the number of topplings at a site in this model can be arbitrarily large. If you start with lots of heights 2, then that can topple many times, because particles will come from above and it will topple many times before it goes down. So, the number of topplings at a site is not bounded. So, this coefficient is not there, there is no rho term, rho squared term. If you do not have a rho squared term, then of course, the universality class of this phase transition changes. Okay. So, this particular model corresponds to this stuff with rho squared coefficient 0. Also, there is no coupling to the phi field. There was a noise field, but the equation for n was autonomous. So, I did not have to worry about phi field, which is the same as saying the conservation law is not very important for me for these models. And so, this coupling coefficient was also 0, 0, 0, and then this equation, since it is not coupled, it does not come into picture, I do not worry about it. And so, the equation is much simpler. But even with this simpler system, you have fairly complex behavior. Okay. But let us go back to the model. So, I started with sand grains, they toppled, there was some stickiness also. So, it was not clear to me a priori that the model was so bad. I was not setting lots of terms to 0 to begin with. I thought I started with a fairly decent looking model and not a pathological model. Okay. In particular, in this particular problem, what we find is that there is a fixed point corresponding to directed percolation, but it flows away to another fixed point, which is this SOC fixed point. And this is quite contrary to the usual interpretation of this Grasberger-Jensen conjecture, which says that everything flows into directed percolation, but nothing flows out of directed percolation. Okay. So, how can you have flows which are directed out of this point into something else? Aren't those operators already well studied and identified and defined and looked at? Okay. So, the point is that one can learn something from these field theory descriptions, but only if you have a good insight into the behavior already. It is very hard to look at the formal description and then manipulate the functional integrals and get very far with that picture. Okay. Another thing which we realized after studying this model. So, of course, we had written this paper in 2002, I described to you, where we found that something goes into directed percolation universality class. In fact, the title of the paper was that the generic behavior of Sandpile models is the directed percolation universality class, which is perhaps we are willing to admit not fully true now, because then we did not realize that something can go out of there into something else. So, there what was happening was that some model was flowing into this directed percolation universality class, and now it is the opposite case. So, what is the difference? Well, it is the difference in the definition of the two models. In one of the models, we said that at each site in one avalanche only one toppling occurs. So, the number of topplings per site was constrained to be 1 or finite. Okay. So, then it looked like it can go into directed percolation universality class. But in these models, the number of topplings per site can be as large as you like. So, that makes it different. That is the difference between setting b equal to 0 and not b equal to 0. But so, in these models you can change the maximum height, instead of 2, 3, put it 2, 3, 4, whatever you like, but that will not change the value of b. B will always be 0 in these models. That is not clear from a very naive field theory kind of description of the problem. There they say you write down all the relevant terms which are allowed by symmetry, then I suppose then you look at all, and then drop out all the terms which are irrelevant, unimportant, and analyze the rest. So, I guess somebody will say that there is a particular symmetry in the model which does not allow you to write down this rho squared term. But that is a very difficult to see, it is a subtle symmetry, it is a hidden symmetry of the problem. So, maybe I should know that there is a hidden symmetry in this model, But if I didn't know it, then I would write down a rho square term and I will analyze the problem and I will get wrong results or misleading results. Not wrong, but misleading. I have to interpret them suitably, and if I don't interpret them carefully, I will get wrong conclusions. So, that's the carry home message from all this, is that one has to be very careful in understanding the field theory treatments, and if you study explicit models, you can learn much more by studying simple cases and extrapolating from there.
Is it possible that rho square term is coefficient is sufficiently small and it's over?
No, because any coefficient here you can rescale and then it becomes order 1. Because this rho squared, yeah, you can absorb the. Okay, so I think, yeah. There is no question, then we can stop right here.